Hey Sam, we know what we're doing now.
Feeling better too. Okay. Over R squared. Okay, we have to find E for both this and this, since it's a halfway point. Okay, so we're going to go with K, which is 9 times 10 to the 9th unit Newton per Coulomb. Am I right? Somebody help me. Josh, pay attention.
Newton meter squared per Coulomb squared.
Okay, so E is K times Q. Now Q is going to be the 2 stationary charges, but
Yes.
one at a time. So we'll do the positive one first. So it was KQ over R squared. So the distance between them is going to be 1.25 meters. And that'll be a quantity squared. Okay. So my meters squared is going to cancel. Oh, so I'm going to convert this millicoulomb here to coulombs. So I can cancel a coulomb. And then, what do you get for this?
What?
Anyone have an answer for the E with relation to the positive particle?
5.8 times
7.
10 to the 6. And it should be Newton coulombs.
10 to the 6?
Newton per coulomb.
You got 10 to the 6?
Yes.
I really didn't make it. Sorry.
Oh!
It's because
It's not millicoulombs in the problem,
times
it's coulombs.
one. No.
Okay.
Yeah, it's just
So
times
that's
one. I was
fine.
really confused over what this
Oh, because I was using my drawing instead of the right drawing. So 10 to the 9.
5.8 times 10 to the 1, 2, 3, 4, 5, 6, 7,
I think
8,
it's
9.
9.
10 to the 9.
5.8, 2 significant figures times 10 to the 9 Newton per Coulomb. And then doing it again for the negatively charged particle with a 2 Coulomb magnitude. 9 times 10 to the 9 is our constant.
I was really tired.
Times
Coulomb
2
squared.
coulombs.
This stuff.
The same distance because it was placed in the middle of the field. And what do we get?
1.2 times 10 to the 10th Newton per coulomb.
Okay. Now what do we do with our 2 E's now that we have them?
Put that. Wait, no. Figure out.
Okay, we need to figure out vectors. So
Yeah.
we know if we should add, subtract, do what. So with respect to the positive charge, which way is our little test charge going to move?
To the. It's positive, right?
The test charge is negative.
Oh, then it's going to move towards the left if we're.
So it's
okay.
going to go left. And we're calling the left negative probably.
Yes.
Okay. And then,
That's also going to move to the left.
okay. Okay, so we're going to add them up. Negative 5.8 times 10 to the 9th plus a negative 1.2 times 10 to the 10th
And
units.
that'll be negative 7.0 times 10 to the 19th Newton per coulomb.
If you add those, it's plus a negative. It's not times.
Oh, yeah, hang on. I
So
messed that up. 1.8 times 10 to the 10th Newton per coulomb.
Negative 1.8 times 10 to the 10th. Significant figure wise 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 7, 8, 9. We're significant here. 2, 8, 7, 1.8. Okay, good. And that's good significant figures too. So, units Newton per Coulomb. And it's negative because it's to the left. Alright, so what's my question again? Now that we've done all that, we don't even know what we're doing. What is the force it would experience at that point? So now, I'm going to erase this significant figure craziness right here to find force. So we know how E relates to force, right? With, E equals the force divided by the test charges and magnitude. That's a positive test charge, so we don't want to use that probably. Let's see, what did I do?
I used negative 6.6 times 10 to the negative 4. I don't know where
I guess
got
we
that
will.
number.
I don't know why I put positive test charge there. I guess we'll just go with test charge. Okay, so we know E, we know the test charge, we can solve for force, which means multiply them together, negative 1.8 times 10 to the 10th Newton per Coulomb times negative 0.66 times 10 to the negative 3 coulombs. So the force is what? And you
Negative
have
1.2 times 10 to the 7 newtons to the left.
That's because that's what the book says. It says Q0 is the Q sub 0 is the magnitude of the positive test charge.
Huh.
F is the electrostatic force experienced by a positive test charge that is placed in the field.
Okay.
Oh, I was
so-
going to ask you that. You don't know what that is? It looks like one of those little terrariums.
Can I go blow my nose?
Yes, that is a
Looks like
big jar of
a
iron
little
filings,
snap
which
pencil
somebody,
box.
possibly Nick, your mother, gave me that. Somebody's mother gave me that jar, so we're going to play with it today.
So it's magnetic?
One would hope.
One would
Well, let's
hope.
test it.
That was,
Wait, wait.
It said fillings. I was like, wait, when you get cavities, is that what it means?
Whoa, look.
It is.
Hang on, no,
magnetic.
don't move it away. Hold it down.
Filings are actually, or
Oh,
fillings
that's
are mercury.
cool.
Filings are iron. They're
Isn't
just-
mercury bad for you?
Yes, that's why metal fillings are bad.
Why did
So
they
you
put it in
shouldn't
our
live in one?
mouths?
That would
dropped
be a
it.
good
Right,
question.
where is it?
Well, my great pulpal is
Ah.
86 and he has fillings, so can't hurt you that bad.
Just makes all your food taste like mercury.
Huh?
Okay, so
What about gold fillings?
gold is very non-reactive,
Wait,
so
is it actual gold or is it like color?
you can get fillings that are actual gold and they're safer than mercury, but
They're
obviously
just like-
way more expensive.
$3,000.
Yeah, but safe. So
Why would
did we
someone
just
want to
finish
get
that
a
problem? I'm
metal
so out of it.
filling anyway?
I think we did. We're done. Let's look at problem number
The
9.
metal feeling or filling is cheap.
Alright, listen,
Cheaper.
number 9, since we actually somehow managed to accomplish that problem, even though I seem to be.
Wait, hang on, we didn't
I
finish it
actually feel
yet.
better now that you opened that door
Did we?
because it cooled off in here, but we can't annoy the other class probably. Yes, that's good.
Is that the end of the problem?
I think it is, because it asked for the force. We know the force is
That's what I
directed to the
got.
left.
But I had to look at the answer key.
So if you just find both E's, then you can solve for force. Works for me. I don't see anything else you need to do. Make sure that when you have a force, it's a vector quantity and you tell the direction, which is obvious because it would move to the left to be attracted to its like charge and to be repelled away from its, or to be attracted to its unlike charge and be repelled away from its like charge. So, does everyone need a minute to hack away at that and make sure I'm right.
Did you know that these calculators you can figure out velocity and significant figures and all kinds of stuff?
Really?
Yeah.
I would never trust a calculator for your significant figures.
You should
Because
be able
the
to
thing
figure out
is-
Sure,
velocity.
we tested it a little bit. And
How did you test it?
You go to apps.
And there's a significant.
You can get
figure
apps on your
calculator.
calculator.
There's apps.
Oh,
You can
so
go on
it's
the internet on that.
You can.
Yeah.
No, you can.
Yes, you
I
can.
don't
They
believe
told.
that.
I promise. I saw this kid go on the internet.
I don't believe
He went on
that.
Google on it.
Then you can't use it at the
What
SAT.
is it called?
Science tools.
I'm not even joking.
No, I know. What's the thing called?
But it wasn't. It was nicer than ours.
Oh.
It wasn't the same.
Oh, a better
Is it
calculator.
Science ESFR?
It wasn't this
What?
kind of calculator though. You can't go on the
It was
internet.
the same
Trust,
brand?
trust me.
Okay, let's talk about problem number 9, now that I feel better. Draw an
Whoa!
electric field generated by 3 stationary charges that sit at the vertices of an equilateral triangle and all have a positive charge.
Significant figures calculator? Unit converter? Vector?
Significant figures aren't that hard. Use your own brain, don't trust it.
Yeah.
Okay. So we have a triangle, we've got,
Josh.
pay attention, I'm already not.
Okay,
paying
stop showing me
attention.
stuff. I'm trying to pay attention.
Alright, listen, you guys will have to figure out the lab today because it's kind of an experiment. Alright, they're all equal, they're all positive. Equally positive. So how would I draw the field lines? Well, what's the rule about where the arrows originate and go?
These
To
guys
start,
hungry.
Oh, they all go away from each other because
Okay.
they're positive.
and they're all equal, so they have the same number of lines. Now do the arrows go into positive or out of positive?
Out.
Okay, arrows start at positive and go toward negative, in this case.
Do 29 out of each particle.
But you have to have even, have some sort of,
29 and a half.
You can do that without going to
So how, is 29 and a half even or odd? Or is it neither
not.
one?
it's not a
0.5.
number. Okay, as bad
Like-
at drawing as that is, they should point. So what if
That's what mine look like.
oh, and that's what it asks next. What is the magnitude of the electric field at the very center of the triangle?
Shouldn't it be like 0? 'Cause-
Zero, because obviously it would be equally repelled away from, those are not field lines, they're just arrows showing force. They would be equally repelled from everything if you put a positive test charge in there. So you have a magnitude of a 0 electric, or charge at the middle field.
It's like
I'm making no sense. That's terrible. Would anyone like to say something sensible about why it's 0 in the center of that triangle?
Because they're all like it's all pushed in the same direction. Like if it's
Okay.
positive, they're all
The
pushing away
forces
from it,
cancel
and
out.
it's in the
The
middle.
forces cancel out. That is an excellent thing to say there. Number 7. The second orbit for the only electron in a helium plus ion. So what do we have if we have a helium plus ion? How many protons are in a helium?
Helium.
2 protons. And how many electrons would normally be in a helium? 2. But if it's a helium plus, then what happened?
One left.
Yeah.
1 left, so
It got
we've
tired of
one
sitting around.
electron. The second orbit for the only electron in a helium plus ion has a radius of 5.29 times 10 to the negative 11 meter. What is the speed of the electron in that orbit? It has 2 protons, each with this proton charge, 1 electron with the electron charge. It gives you the mass of the electron, which is definitely ridiculously small. And we need to find, and this is kind of, because we all know electrons don't orbit like the Bohr model, like a planet, right? But that's what we're assuming here, and I give you
Josh is like,
permission to assume that.
Your battery is running low.
Turn her off. We'll switch before we